am T. Kavitha, Assistant Professor, Department of Mathematics. Today we are going to see the case study problem. This problem is in transportation problem. This is based on optimal distribution of goods. That company overview, ABC Distributors operates 3 warehouses and supplies products to 4 retail stores. The company wants to minimize the case of shipping goods from the warehouses to stores. The data are given here. Supply at warehouses. Warehouse A is 100 units, warehouse B is 150 units, warehouse C is 200 units. Demand at retail stores are store 1 is 80 units, store 2 120 units, store 3 150 units, store 4 100 units. And the data are from stores to warehouses. Warehouse A to from store A S1 to warehouse A $4. Then warehouse A to S2 6, warehouse A to S3 $8, warehouse A to S4 $4. Then warehouse B to S1 is $5, warehouse B to S2 is $11, warehouse B to S3 is $9, warehouse B to S4 is 7, warehouse C to S1 is $10, warehouse C to S2 is $8, warehouse C to S3 is $6, warehouse C to store S4 is $S4. In this problem, our objective is minimize the total transportation cost while satisfying the supply and demand constraints. First step, we have to formulate the problem as a linear programming model. That is, from warehouse A, warehouse B, warehouse C, these data is given in the data in this problem, and supplies are given for warehouse A is 100, warehouse B is 150 units, and warehouse C is 200 units, and warehouse C is 200 units. Then the demand for store 1 is 80, and store 2 is 120, and store 3 is 150, and store S4 4 is 100. This is the mathematical formulation of the given transportation problem. Then we have to convert it. Then we have to solve the this problem to find the initial basic feasible solution. There are 3 methods of here. First one, northwest corner method. Second one, least cost method. Third one, Vogel's approximation method. Here we have to use Vogel's approximation method for better initial basic feasible solution. The first we have to analyze the problem. The total supply is 100 plus 120 plus 200. The total is 450. And also the total demand is 80 plus 120 plus 150 plus 100. Here the total demand is 450. Therefore, total demand and total supply is equal. Therefore, the given problem is balanced.
In the problem, one objective is minimize the total transportation cost while satisfying all the supply and demand constraints. Steps. First step is formulate the problem as a linear programming model, that is from to warehouse A, warehouse B, warehouse C, store 1, 4, 5, 10, store 2, 6, 11, 8, store 3, 8, 9, 6, store 4, 13, 7, 4, supply 100, 150, 200, demand 80, 120, 150, 100. Solving methods are northwest corner method, second least cost method, third Vogel's approximation method. Here we have to use Vogel's approximation method for better initial basic feasible solution.
Step 1. Total supply is equal to 100 plus 150 plus 200 is equal to 450. Total demand is equal to 80 plus 120 plus 150 plus 100 is equal to 450. Here, total supply is equal to total demand. Hence, the problem is balanced. Step 2. Calculate row and column penalties. Each penalty is equal to second lowest cost minus lowest cost in the row or column. Penalties are row A cost is equal to 4, 6, 8, 13. 6 minus 4 is equal to 2. Row B is equal to 5, 11, 9, 7. 7 minus 5 is equal to 2. Row C is equal to 10, 8, 6, 4. 6 minus 4 is equal to 2. Column 1 is equal to 4, 5, 10. 5 minus 4 is equal to 1. Column 2 is equal to 6, 11, 8. 8 minus 6 is equal to 2. Column 3 is equal to 8, 9, 6. 8, 6 is equal to 2. Column 4 is equal to 13, 7, 4. 7 minus 4 is equal to 3. Step 3. Select highest penalty. Here the highest penalty occurs in column 4 equal to 3. Look at the minimum cost in that column. Minimum cost is equal to 4 at C in store 4. Allocate minimum 200, 100 is equal to 100 units from C store 4. Now we get supply at C is 200 into 100. Demand at store 4 is 100 into 0. Eliminate column 4. This is the new table. Penalties for the new table is row A is 6 minus 4 is equal to 2. Row B is 9 minus 5 is equal to 4. Row C is 8 minus 6 is equal to 2. Column 1 is 5 minus 4 is equal to 1. Column 2 is 8 minus 6 is equal to 2. Column 3 is 8 minus 6 is equal to 2. Highest penalty is equal to 4 in row B. Minimum cost in row B is equal to 5. B store 1. Allocate minimum 150, 80 is equal to 80. Now we get supply at B is 150 into 70. Demand at store 1 is 80 into 0. Eliminate column 1. This is the next table. Now the penalties are row A is 8 minus 6 is equal to 2. Row B is 11 minus 9 is equal to 2. Row C is 8 minus 6 is equal to 2. Column 2 is 8 minus 6 is equal to 2. Column 3 is 9 minus 6 is equal to 3. Highest penalty is 3 in column 3. Select column 3. Minimum cost is equal to 6 at C store 3. Allocate minimum 100, 150 is equal to 100. Now we get supply at 100 into 0. Demand at store 3 is 150 into 50. Eliminate row C. This is the next table. Penalties are row A is 8 minus 6 is equal to 2. Row B is 11 minus 9 is equal to 2. Column 2 is 11 minus 6 is equal to 5. Here highest penalty is 5. Select column 2. Minimum cost is equal to 6 A into store 2. Allocate minimum 100, 120 is equal to 100. Now we get supply A is 100 into 0. Demand store 2 is 120 into 20. Eliminate row A. This is the next table. Select minimum cost 9 B to store 3. Allocate 50. Store 3 is 50 into 0. Supply B is 70 into 20. Then B is store 2. Allocate 2. This is the final table. The initial basic feasible solution using Vogel's approximation method gives a total transportation cost is equal to 100 into 6 plus 80 into 5 plus 11 into 20 plus 9 into 50 plus 100 into 6 plus 100 into 4 is equal to 2670. Thank you.
Finally, in VAM method, we get the initial basic feasible solution that A2 is 100, then B1 is 80, B2 is 20, B3 is 50, and C3 is 100, C4 is 100. This is the final allocations of this given transportation problem. The initial basic feasible solution using Vogel approximation method gives a total transportation cost. How to calculate the transportation cost total? 100 into 6 plus 80 into 5, 20 into 11, 50 into 9, 100 into 6 plus 100 into 4. We sum all this value, we get the value $2,670. This is the optimum transportation cost for that company. Okay, thank you.